What are you talking about?
Come on in, everyone. Come see my Brad.
Hey, Professor Young.
Hey, Micah, how's it going, bud?
I'm doing okay. I wanted to let you know, I missed class on Monday. I had busy Saturday and Sunday because well, I think I shot you an email, but I had to take my grandma to urgent care in the hospital all day, and then like the day after, so I missed what is it? I think the test that was due on Sunday. So I was wondering what we could do about that.
Uh, yeah, let me think a little bit on
Yeah,
that. I'll probably just open it back up for you. I had a couple other people have similar problems, but make sure
yeah.
you don't miss them in the future, of course. How's your grandma doing? Is she okay?
Yeah, she's okay. What happened was I think her stomach was hurting. And like when she ate stuff, she was having like a really bad acid reflux. So I took her to patient first, and then they did some scans on her, and they said she was dehydrated and she started having like kidney damage. So and she had like a blockage too. So they recommended I went to a Beach General immediately. So I took my grandma there. So I was with her, I think from like 2 p.m. to like 1 a.m. like all day, and then they were running some tests on her, and the doctor like they admitted her,
Oh, God.
and I'm trying to think what
I'm glad you
happened.
got her in, though. I mean, if she
Yeah,
needed
yeah, it was
more.
just like kidney damage and stuff, and then at one point her IV fell out, so she lost a bunch of blood and she had to stay on longer. But she got
Oh.
home yesterday, so yeah,
So
she's doing
it
other.
was not the chicken that you cooked that made her sick, though, right?
Oh no, yeah. But it's kind of funny. She just got when she got out of the hospital, she started doing yard work again and cleaning up the house and taking care of her chickens. So
Yeah.
yeah,
Yeah.
it's pretty
Well,
cool.
you can't just stop everything just because you're sick or dying.
Oh yeah, that's true.
Tough people, man.
Yeah,
Well,
but
I'm glad she's doing better.
yeah. But what happened was I usually grind out physics from like Friday to Sunday. So on Sunday I wanted to take the practice test, but yeah, that happened. So and I know you already were pretty generous and you allowed us to take it over like the weekend.
Right.
So yeah, but yeah,
That
sorry for having you extend it further.
that was the actual face-to-face test you missed then instead of the.
Yeah, but that was the one that you said we could take it home with the big mirror behind us.
Oh, yeah, so that's the face-to-face. I'm going to go ahead and
Yeah.
set it just to get you to knock it out.
Okay,
Off
thanks.
Sunday if that's cool with you.
Okay. So what's the due date for it?
For you,
There again?
I'll make it due Sunday at 11:59 p.m.
Okay, it's on your 11:59. Okay, cool. Thank you. Yeah, appreciate
No
it.
problem.
So yesterday and today I've been grinding all the work that I missed. I've been going back through chapter 19 and 20.
Hmm.
Yeah, and then I have all the Pearsons to do that. But like literally this week, I'm just giving all my time to like physics. So
Yeah, so
yeah,
you just gotta dedicate a day to it every now and then. Try to
yeah,
get back on the schedule where you're, doing some physics every day. That's better for you, but until
yeah,
do what you gotta do to get caught up.
yeah. Oh, and like sorry, I just lost like a lot of sleep too from helping my grandma with that. I think I was trying to sleep in, and then my mom freaking called me really early in the morning, and I couldn't sleep for the rest of the day. And like
Right.
yesterday, I started developing a fever because I wanted to sleep in, but like my grandma's sink it freaking broke, so there was people that needed to come and fix it, and she kept waking me up. So
Well, that's
like
not
I
helpful.
yeah, like I had fever, I was trying to sleep, and then people didn't want me to sleep. So yeah,
Gotcha.
yeah,
All right.
sorry about
Well,
that.
I just made the test available to you until 11:59 on June 30th. So hopefully you can
All
knock
right,
it.
thanks, Younger. Yeah.
All right. See you, Micah. Of course, we still got class. I see I got Aaron and Micah and Rhea here. Anybody have any questions before we get started? I appreciate you three showing up. Of course, when I schedule the time, I try to schedule it during lab time so y'all have the time available so that everybody could attend. But it looks like the same thing's gonna happen where we're only gonna have one or two
Uh,
people.
did we do Gauss on Monday?
Yes, I finished
Okay. Okay,
Gauss's
yeah.
law.
So
I've
we're doing
adjusted
electric.
the dates too.
Okay, cool. So we're doing electric potential
Yeah,
today then.
chapter 23
Okay,
now.
yeah, that's cool. Yeah.
All right. All right, so what I want to tell you about electric potential is sort of like what we did in chapters, if you had me for 241, or if you had Giancolli's book for 241, you know that when we finished chapter 6, which was gravity, we went into chapter 7, which was work, and then we went in chapter 8, which was mechanical energy. And that presented a new way of solving physics problems that didn't require vectors, that required something called energy. You could still get back the vectors. So for instance, you could use conservation of mechanical energy to calculate the change in speed from over some distance. And then you could use kinematics, of course, to figure out what that acceleration is. And then, of course, acceleration is a vector quantity, so you can make a vector out of that. And then once you have a vector out of the acceleration, you can use Newton's second law to get forces, all that sort of stuff. So there is actually a way to do everything that we did in the earlier chapters 1 through 5 by doing them with energy methods without vectors. But ultimately, if you want vector quantities, you can still get them. So now we're going to do the same thing with electricity. We start off with Coulomb's law, and specifically Coulomb's law for the electric force. And Coulomb's law for the electric force basically stated that the electric force was either attractive or repulsive, depending on the two charges that were being examined. If the two charges were like, both positive or both negative, for instance, then they repelled one another, so that was a repulsive force. And if the two charges were unlike, one positive, one negative, for instance, then the force was attractive. And that force was directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Now, the other part, which gives you the vector quantities, you actually have to know the direction in addition to the magnitude. So the Coulomb's law formula gives you the magnitude, but then you got to realize that along with the formula says, along with the formula comes the description of the direction. And the direction is along a line connecting the center of charge of the two charges. So if you have 2-point charges, it's just along a line connecting the 2-point charges. If it's two finite charges as opposed to point charges, then you have to find the center of charge of each of them and then draw a line connecting the center of charge of each of them. And then the force will be along / parallel to that line. Now, whether it points that way along the line or that way along the line depends on whether it's repulsive or attractive, but that's the way you do it. And of course, I told you never to put your charges in and that sort of thing, never put the signs of the charges in, that sort of thing, and then just use your understanding of the physics of electricity and magnetism to work out the direction as opposed to, once you decide it's, for instance, attractive force, then if you're saying it's an attractive force on charge Q1, then the force would act along a line from Q1 towards Q2. If it was repulsive, then it'd act along the line from Q2 to Q1. Okay. Now that was fine. That was a force equation that required forces, but we were also bothered by the fact that it conjured up the idea of action at a distance. So for instance, it was as if this little point charge here reaches out across space to this little point charge and grabs it some way, even though there's nothing physically connecting them. Newton had the same problem when he introduced the law of gravity, but in that case, he knew that he could get a lot of work done. He could, for instance, explain Kepler's 3 laws. He could actually derive them and build on them. So he's even able to go farther and say, in fact, there's only 2 types of forces in nature that can create what we call closed orbits. So elliptical, circular orbits and stuff of that sort. And actually it turns out to be all conic sections, but actually those types of forces were 1 over r squared, which is what Coulomb's law is, or F equals kx, which is Hooke's law. So Newton was able to do a lot with it. And even though I didn't understand necessarily how it reached across space, he knew that it was consistent with what the experiments showed. So he just ran with it. And later we tried things. I don't know why I'm yawning. Anyways, well, later we tried things. We tried to introduce, for instance, an aura around one of the masses, for instance, in gravity. Remember, Coulomb's law was proportional to the product of the charges and inversely proportional to the square of the distance between them. Newton's law of gravity was proportional to the product of the masses and inversely proportional to the square of the distance between them. But Newton's law of gravity was in fact always attractive, never repulsive. That's the major difference. But again, it had the same sort of definition of what direction it would point. It's along a line connecting the center of masses of the 2 points as opposed to the center of charges. And it still had the action at a distance issue. So it was conjured up that perhaps one of the masses of the two masses could act like a source for some aura around it. So if you said, for instance, Newton's law of gravity says G m1 m2 over r squared, then you could say m1 is the source of the aura. And then m2 would just be something that feels the aura. Okay. We did in fact try that. It doesn't work out very well with gravity. I mean, you can do a lot of stuff, but it doesn't ultimately solve the problem. That was left for Einstein after he had published his general theory or his special theory of relativity. He went on to publish a general theory of relativity 10 years later. In that case, he actually addressed the big picture of gravity, and we saw that gravity, in fact, wasn't a force, but rather a puckering of four-dimensional space-time, so that particles were trying to go as straight as they can, but space itself was bent due to this quote-unquote aura type thing, which we now interpret, at least in gravity, as a four-dimensional space-time on which mass causes dimples. Okay, so when we did it with electricity and magnetism, when we imagined an aura being around one charge and then the other charge feeling it, that did work out, and that aura became known as the electric field. So if you look at that, I'm going to go ahead and share my screen now. Well, once I turn my screen on, that would be helpful. But I'm going to share my screen, and what we did there is we imagine, for instance, that you had a Coulomb's force, F equals, let's use K, even though I hate that multiplier or that constant, but F equals K, big Q, little q over R squared. That would be Coulomb's law with the additional rule about the direction and the repulsion versus attraction, all that good stuff. But that's basically Coulomb's law. And what we do is we picture the big Q. We picture the big Q as the source of the aura, and the little q is the test charge that senses the aura. Okay. And in doing that, we know that, hey, if I say a charge big Q causes an aura, then that's not consistent with reality to suggest that a charge of little q wouldn't also create an aura. So to take that into account and to make sure we're not counting things twice, what we had to do was actually imagine taking the force, which was K, big Q, little q over R squared, and dividing out the actual test charge, little q. But when we did that, we had to make sure little q hadn't altered the field so much. So what we did is we imagined that division process where we divided the force K Q, big Q over Q, or excuse me, K big Q times little q over R squared. We're going to divide that by little q. But in addition to doing that, we're going to only do it by taking the limit as little q goes to 0, because we don't want, for instance, to imagine a electric field that's been created as a result of both big Q and little q, and then calculate what the force on little q is, because we'd be counting Q's force on itself, which doesn't make any sense. Okay, so now that my iPad is open, I am going to close the document that I'm currently looking at, and I'm going to open another document. There's a little process on this. I thought I'd already done it, but I clearly did not. So this is actually going to be, instead of 242 N01C, it's going to be 242 D01B. So I'm going to change that name. And instead of June 25th, it's for June 26th. So the file, when you go, for instance, to my Google Docs page for 241, the file will be called PHY242D01B _ 06262024. So that's the new document for today's notes. I'm going to actually make a duplicate of it, so I'll have it to copy tomorrow when I do my other class. So now that I have this open, I'm going to go ahead and share my screen. So I click on share screen, iPhone, iPad. Now I got to select on my iPad, just select my computer, does that. So now let me put in words exactly what I was saying. So we had Coulomb's law, and that was F is equal to, again, we could use K, big Q, little q over R squared, and we have Newton's law of gravity, which is F is equal to big G times, let's say, big M, little m over R squared. So you see how they're similar. Of course, the main thing is they're not similar in that gravity is always attractive. If you have mass, then you're going to be attracted to another gravitational source, in other words, another mass. But in Coulomb's law, if the two charges are the same, then they repel. So if they're both positive or both negative, they repel. But if they're opposite charges, one positive, one negative, then they attract each other. And they still act in the same way along the line connecting the center of mass of M and M or the center of charge of big Q and Q. So that's what that was. Now, what we ended up doing to deal with that is we imagined an aura. That's the word I'm using, which actually becomes what we call an electric field. And as I mentioned to you guys before, a field is basically imagining some portion of space. So it could be all of space, all the universe, for instance, or it could be just, for instance, a classroom or a little segment in a lab or a little, rectangular three-dimensional area in a lab. But either way, in that space that you think is relevant, you're going to assign a coordinate system that has, for instance, an origin. You'll choose coordinates, usually, well, you can choose any coordinates you want, but it's a lot more complicated to work with a lot of the operations if we're doing operations other than in coordinate systems like the Cartesian system. So we have x comma y comma z is a point in that space or that part of space. And to each of those parenthesis x comma y comma z, close parenthesis, each of those points was assigned a value. In the case of the electric field, which is a vector quantity, you would actually assign a vector to each x, y, z. It would have both a magnitude and direction, or it'd have a y component, an x component, and a z component, or maybe it would have an r hat component because it was in spherical coordinates, and r hat depends on theta and phi, as well as r, the distance away, is parallel to the r hat. So we can do all that stuff. But the main thing is to create that aura. We said, okay, well, what we'll do is we'll imagine one of the charges, big Q, to be the source. And we're going to take Coulomb's law, which is big Q, little q, K over R squared. And what we're going to do is divide out the test charge. So this guy is pretending now to be the test particle. And this one is called the source of the field or the aura. Okay. But as I said, when you actually do this, when you imagine an electric field created by a charged big Q, then it's a little hypocritical to suggest that, yeah, you can create an electric field with a charged big Q, but this other special charge, this test charge, that's not going to create an electric field. No, that's bull. It definitely has to. If you say one charge causes an electric field, then all charges have to cause electric fields, positive or negative, in other words, non-zero charges. So in order to take into account the fact that the other charge would actually create an electric field as well, we want to imagine a scenario in which the charge little q has such a small effect on the field that it's not relevant. So in order to do that, we physically imagine taking the limit as little q approaches zero. and then dividing the force, Coulomb's law, Q over R squared divided by Q. And ultimately what that gives us is the formula, which is KQ over R squared. But like I said, the way I prefer to write it is Q over 4 pi epsilon naught R squared. And then of course it still has that description of how we get the direction and all that stuff. Remember, we actually were able to address that by saying, okay, if we want the electric field at P, then the direction can be given by a vector from the origin, pointing from the origin to the point P, and a vector pointing from the origin to the charge big Q, then that vector RP minus RQ is actually equal to, or is actually parallel to that line that we want to use. And in fact, it points from the charge Q to the point P. So if the charge Q is positive, it's automatically going to point in the right way. If the charge is negative, you could actually stick the negative sign in and it would reverse the direction of RP minus RQ and then therefore point the right way as well. So in order to do that, now what I'm going to do is take this R squared that I have there, and realize that's supposed to be the distance between Q and the point P at which we wish to know the electric field. So I'm going to erase that and stop calling it R squared, and realize that by me multiplying by RP minus RQ, I introduce another factor of R. In other words, the magnitude of RP minus RQ is R. So if I left the R squared in the bottom, that R, one of those R's would cancel out and the force would go like 1 over R, and that's not good. So what we do instead is we say, okay, let's go ahead and acknowledge that we're taking the magnitude of a vector. And that magnitude is the magnitude of RP minus RQ, like that. But now that we added the extra RP minus RQ up top, we have to now raise that to the third power instead of the square power. So that actually gave us our electric field as a vector quantity. So we can go back now, once I've written in red, I can put a red vector symbol over the E to just show that, hey, at least that last result is okay vector-wise. Now, I wrote this to stand out in red, specifically so it would stand out, but now that I'm using that sort of red vector symbol to indicate that I've taken it into account, the vectorness, I'm going to go back and change this to just plain blue. So this is the limit as Q approaches 0. So all of that is a little bit of background. And like I said, I'm trying to switch to a non-vectorial basis. And to do that, I'm going to think in terms of potential energy and that sort of thing. So let's step on to that, and you'll hopefully see the parallel between going from force to electric field and between going from, or as compared to going from the electric field to the electric potential. Okay, so there's a parallel there. So what we do know from chapters 7 and 8 is that the change in potential energy, U, well, let's go back a little bit. If, dang it, if a conservative force exists, then we can define a scalar potential energy U such that the integral, well, let's say it this way. such that, well, I'll go ahead and say what it is, such that the force is equal to the negative gradient of u. Okay, that's the brute force way of what we're talking about here. And this gradient is a vector operator, and it's normally written like this upside down triangle with a space and then says equal. And what we're supposed to do is write I hat first and then take a derivative but leave a space with respect to x. So we're doing I hat, and then we're imagining whatever's to the right of that operator, that del operator, or nabla as they call it in Portuguese, whatever's to the right is going to be hit by a derivative with respect to x, and then that's going to be multiplied by I hat. It's also going to be hit by a derivative with respect to y, and then that will be multiplied by j hat, and it's also going to be hit by a derivative with respect to z, and then that's going to be multiplied by k hat. So that's actually what the gradient operator is. I hat partial with respect to x plus j hat partial with respect to y plus k hat partial with respect to z. And if you want to do that in a coordinate system that doesn't use Cartesian, that's not x, y, and z, then there's a lot of work you got to do to convert to what it is, or you at least have to look it up. So if we have a conservative force that exists, then we can define a scalar u. And what we learned from that is, for instance, in the case of gravity, that was a conservative force. And if you look at Newton's law of gravity and Coulomb's law of electric force, you see that they're so similar, you'd probably suspect that since Newton's law of gravity is conservative, F, Coulomb's law, is also conservative, and you'd be right. Okay. I will tell you the test for conservative force really is if the cross product of F is identically 0, then F is a conservative. I said cross product, I didn't mean that. So force. What this quantity actually is, it is a cross product, but it's a cross product of that del operator, that gradient, crossed with F. And this quantity, this gradient crossed with F, is actually called the curl. That's the curl of F. So if you actually compute that curl of F, which requires, usually you do it with a matrix and then take the determinant of the matrix. But if you compute that and you get that it works out to be exactly the zero vector, meaning you don't have to put in a specific value of x or a value of y or value of z or value of all of those or some part of those, it's just identically comes out zero, then the force is conservative. Okay, so that's something you can do with Newton's law of gravity. You just, of course, have to convert the r to square root of x squared plus y squared plus z squared, and then you got to convert that all to magnitudes in certain directions. So you have to make it into components and stuff like that, and you would confirm that both Newton's law of gravity and Coulomb's law are conservative. So once we have that, what we know is that we can define the potential energy is defined as delta U is equal to the negative of the work done. And actually, let's go ahead and clarify this a little bit more. I'm going to write this delta U a little bit more explicitly. I'm going to say specifically delta U, which is U final, which I'm going to assume U final would be the potential energy at a point we call B, minus U initial, which I'm going to assume is the potential energy at a point we call A. And that change in potential energy, delta U, is U final minus U initial, is equal to the negative of the work done by the conservative force. So this is very specific. This is the work done by the conservative force. Okay. That's why we have to do negative, because the potential energy is something that we expect to go down when something moves on its own. For instance, if you put a ball up on the top of a mountain, it will tend to stay there. But if you put a ball on the top of a mountain, say, where it's an unstable equilibrium, like this little point right here is, then it's going to naturally choose to move either this way down the incline or this way down the incline. And it's going to end up here or here with U final being less than U initial. So there's U initial up there, and there's U final down here. So things tend to naturally move, meaning on their own without any recourse, on their own from from high potential energy to low potential energy. So we can figure that out by calculating the negative of the work done by the actual force that causes the potential. Because in that case, you're actually pretending like the work is making the object go from the comfortable place to the uncomfortable place. And we're multiplying that by a negative because we want it to be exactly the opposite of what it does. So with that in mind, we actually can compute something very simple like the potential energy. So let's imagine two parallel plates, oppositely but equally charged, like we've already talked about to some extent in class. For instance, we did a Gauss's law for an infinitely large plate and found that the electric field above the plate is sigma over 2 epsilon naught pointing away from the plate, and then below the plate's also sigma over 2 epsilon naught, but in that case it's pointing down, which is also away from the plate. So we had computed that, and then I imagined putting a positive plate next to a negative plate and found out that the electric field between them, since they point in the same directions, both the electric field from the positive plate and the electric field from the negative plate, they both point in the same direction. So when you add them, you get sigma over 2 epsilon naught plus sigma over 2 epsilon naught, which gives you sigma over epsilon naught, right? So that's what we're going to imagine now is we have something like that. So this is going to be, for instance, a section of our parallel plate capacitor. And we're going to imagine this parallel plate capacitor. Again, you don't necessarily know what capacitor means yet, but that's okay. We're going to learn later. We're imagining that we're zooming into a very, very tight place up close. In other words, the plate extends on for some distance below and above like that, okay? And the reason why I want to do that is I want to be able to claim that the plates are closer together than they are from the edge of the plate, so that we basically get that straight uniform electric field in it. What I'm going to do is say this side is the positive plate and this side is the negative plate, and they have a charge of plus or minus sigma. What that means is right here, I got a plus, and right here, I got a plus, and then right here, I got a plus, and then over here, I'm going to have a negative charge, and then a negative charge, and then a negative charge. And the way that,
excuse me, Professor,
yes.
do you mean like charge density?
Exactly. That's the sig. I am actually talking about a total charge on the plate, but yeah, I wrote sigma up there because their charge densities will be the same. Yes.
Yeah, okay, cool.
Yep. And if you're reading along, your book's already given you some discussion about electric field lines, and hopefully you figured out from the text that it explicitly says you imagine electric field lines as if they begin on a positive charge and then they terminate on a negative charge. So you can imagine this electric field line pointing just like this. Now, in principle, they actually have to go on to touch the negative charge and go on to touch the positive charge. But the main thing is they begin on a positive charge and they terminate on a negative charge like that. Okay, so that's what the electric field looks like in that. And we know its magnitude, of course, is sigma over epsilon naught pointing to the right. Now, what we're going to do is we're going to imagine a little positive charge right here, and that's going to be at point A. And then we're going to imagine the same charge, which is positive, being at point B. Okay. And again, since these plates are so close together, meaning we're so far in between the plates that we're way closer to the left plate or the right plate than we are to the top of the plate or to the bottom of the plate or to the front of the plate or to the back of the plate. At least a factor of 10, as I've talked about before. Because of that, we won't have any of this electric field lines bulging out like this, because that's what they do. You did that in your electric field mapping. You saw that the electric field lines basically go straight and are uniform between the plates, but as you get near the top edge and bottom edge or front edge and back edge, the electric field is going to bulge out and do some other stuff. Of course, it's always got to be perpendicular to the conductor, and that's because conductors are equipotential surfaces, and equipotential surfaces are always perpendicular to field lines. All right. Now, what we can do is calculate the change in potential energy, delta U, which would be UB minus UA. That's going to be equal to the negative of the work done. We know that work is equal to the integral of F dot dl, but in this case, the force is uniform. And not only that, the force is actually parallel / anti-parallel, depending on which direction I go, to the line of travel that I'm going from B to A, or excuse me, from A to B. So I can actually say this is going to be the integral of the electric field, which clearly points to the right, and I can solidify that by saying, okay, let's imagine that this is our x-axis and that this is our y-axis, and that this distance from here to here is d. Okay, so my electric field is going to have to be, or excuse me, I wrote electric field there. I meant to write, oh, actually I want that back. Okay. So now what I'm going to do is I wrote electric field here and I meant to write force. So the force is actually going to be equal to, remember, E is equal to F over Q with that special limiting process, but that means F is equal to QE. So I'm going to take and imagine the charge Q. Darn it. I'm going to imagine the charge Q being multiplied by the electric field E, and the electric field points to the right, so that's in my I hat direction. So this right here is the force, and then I'm going to dot that with dx I hat, and I'm going to integrate, of course, from x equals 0 to d. Okay, so I am actually going from x equals 0 to d. So when I do a line integral, and this is something special, you've actually got to make sure the integrand, which in this case is f dot dl, you've got to make sure that's evaluated on the actual path or line that you're integrating along. In this case, there's no x's and y's in the electric field, x's or y's or z's in the electric field or in the force, nor is there any in the DXs or in the DL other than the DX. Okay. So there's no way of taking an equation like y equals 7, which might be the equation of the path that I chose, where 7 is 7 centimeters above the origin or something like that. I don't have to do that because I can't, because the electric field is uniform and it's going to be the same everywhere. But that's generally what you do, is you take any x's and y's that exist in the integrand, and you take the equation for the path you're integrating along, like y equals 7 or y equals x squared, and everywhere you see a y, you replace it with x squared if you're integrating along y equals x squared. Or if you're integrating along y equals 7, then you replace all the y's with 7. That is how you make it a path/line integral. The good news is the majority of the time, people can do line integrals not knowing they're doing line integrals and get the right answers. But as you do this more and more often, you're more likely going to run into instances where you accidentally screw something up unless you know what a line integral is and how to do it. Now, in this case, we're going to go ahead and complete the line integral. And what I'm going to do is recognize that the dot product is a linear operator. We've been working with that already. And that means I can pull the scalar parts, which is Q and E and DX. I can pull that all out in front of the dot product, and then just let the dot product act on the individual vectors, which are I hat and I hat. When I do that, I hat dot I hat is just 1 times 1 times the cosine of 0. So, and the cosine of 0 is 1. So we get 1 times 1 times 1 or 1. Now, the other thing is, since Q and E are constants, they can come right out in front of the integral, and I get QE times the integral dx. And of course, the integral is supposed to be from x equals 0 to d, 0 to d, like that. And from this, I get Q times E times d. So that's what the actual work is. And that means that the actual change in potential energy is the negative of the work being done by that. So when I wish to do that one, I will get the negative of the work. So I will get delta U, which is UB minus UA, which is the negative of the work done. And I'll subscript it like your book does. They put a B and then an A. And when you subscript work or potential energy or electric potential, which we're going to learn in a second, what we're going on is the assumption that this first one is the final point, and the second one is the initial point. Okay, so since we've done that, I can now say this is going to be negative Q times E times D. And that is the change in potential energy in moving that positive charge, which, by the way, I'll say has a charge of positive Q. That's the change in potential energy of moving that positive charge from A to B. Now, notice it's a positive charge that was right next to a positive plate. Do you think that's a high potential energy right next to the positive plate, or is that a low potential energy? You can type that into the chat, or you can just speak it out, whichever one you want. So I'm asking again, at point A, does that positive charge sitting at point A, which is right next to the positive plate, is that a high potential energy for the positive charge, or is that a low potential energy for the positive charge?
I'm gonna.
Shouldn't that be like a high potential?
Yeah, I was thinking the same thing.
Yeah, you're exactly right. Point A is a high potential energy. The reason why is you can think of it like gravity. Remember, if you had me for 241, I said that the hallmark of being a high potential energy place is that you as a human would be kind of scared. Because, for instance, it's a lot higher potential energy for me to be at the top of a telephone pole than it is for me to be standing on a chair, right? So,
Professor,
yeah, go ahead.
well, I was thinking it's a high potential because as it moves from the positive plate to negative plate, it's gonna have a kinetic energy. It's gonna have a speed, right?
Yeah,
Yeah,
that's the
yeah.
hallmark
I,
of it is
yeah, I was
if you're
just kind of
going from high to
skeptical.
low, it will speed up.
Yeah, I was just kind of like hesitant to answer because I remember like last semester it was like reversed or in some case or something like that. Or I was confused about. Oh, and also it's like a high electric potential too, right?
That's where the part that's confusing you, the part that
Oh, okay. Got you.
that's where that part comes in and gets you confused. So I'm trying to stay with potential energy right now because most of us understand that better than we
Mhm.
do potential electric potential, which I'm going to cover.
Yeah.
Does that make
Okay.
sense?
Yeah, thanks.
Now the other part is point B. Ah, crap. The other part is that point B is low potential energy. Okay. So when the charge was moved from A to B, it went from high potential energy to low potential energy. And therefore, the change in potential energy should be negative, which is exactly what we got. So consistent with delta U less than 0 or UB greater than UA being greater than UB. Okay, so that negative sign tells us that, and it makes us feel more confident about what we did. Okay, now that also gives us a result. The result is, hey, the potential energy between two different points in a uniform electric field is just proportional to the electric field, QE times D. So it's the charge times the electric field times D. Now, what I want to do is do the same thing we did with electric field or with force. So before we took F is equal to Q over 4 pi epsilon naught R squared. And we went to E, which is Q over 4 pi epsilon naught R squared. And we did that by dividing by Q. Okay. So now what I want to do is something similar. I want to go from delta U to delta V by dividing by Q. So what I'm going to do is I'm going to say delta V, which can be written as VB minus VA, which can also be written as VBA, consistent with the subscript rules I told you about a second ago. That's going to be equal to delta U over Q, which is the negative of the work done over Q, and we say B to A again, which means we're going from A to B. And that, of course, gives us negative of Q times V times B. Does that make sense? Because we just calculated, well, I'll just say it this way. We get negative Q times E times D divided by Q, which gives us delta V is just E times D. Now, that is exactly the expression we wanted for this particular scenario. But the best thing about this, in my opinion, is that we now have a new understanding of what the units of the electric field are. So for starters, we're going to define a new quantity, delta V, which has units based on what we just wrote here. It has units of delta U divided by units of charge. Well, the units for delta U is just the joule, and the unit for charge is just the coulomb. And we're going to define this to be the volt. Okay. So now we can see that the electric field, if I take this specific equation, everybody see that equation, delta V equals ED? If I solve that for E, then what I get is E is equal to delta V over D. Now we're just looking at this in terms of units or dimensions. So what's going to happen in this case is we're going to take the units of delta V, which is volts, divided by the units of D, which is meters. So what we now learn is that the units of the electric field are also equal to volts per meter, which is obviously the same as newtons per coulomb. But this is the part that's new to us. Okay. Now, this unit of the volt, that is a joule per coulomb, and what you can interpret that is if you had a charge of 1 coulomb and you applied a voltage difference of 1 volt, then what would happen is that charge would move in the direction of decreasing potential energy, such that its potential energy would decrease by 1 volt, or excuse me, by 1 joule. And that's about as much energy as it takes to lift a good succulent red delicious apple from the ground to about the height of a common kitchen table. So a single volt is basically the amount of energy to move a 1 coulomb charge through a potential difference, a potential energy difference of 1 joule. Does that make sense? All right, so from all of this, we now have a new way specifically of specifying this new quantity called the voltage. So what I'm going to do is I'm going to state it right here, and I'm going to state it just like your book does, a couple different ways. We're going to say, for instance, I can say that the voltage at point A is the potential energy at point A divided by a test charge that you put there. So that's one important equation. And then the other one, again, writing it like your book does, the VBA, which means the voltage change in going from A to B, is also going to be called delta V, which is also the same thing as V final minus V initial, which would be VB minus VA. That's going to be equal to, remember, the negative of the work done, but that also happens to equal, based on that definition we just gave for VA, that's going to be UB minus UA over Q. And all of that, of course, is going to be the negative of the work done in going from A to B and dividing it by Q. So this is, in fact, another equation. I meant to write that in blue and box it off in red, but I forgot to change my marker. So that's good enough. Now, the other thing I want to express is that a way of writing this is VBA, which is equal to delta V, which is equal to VB minus VA, is equal to the negative of the work done in going from B to A, or from A to B over Q, which ends up becoming negative 1 over Q times the integral of F dot dl. But that ends up becoming, because the Q is going to be divided into the F, we end up getting the negative integral of E dot dl. So that is ultimately another equation that we're going to use, where I care most about the first 3 parts. So I'll put stars by them. So this part, and this part is very important. And the main result I wanted you to get is that part. Okay. We had already discussed this particular part right here. We had already discussed that when we did this. So this is just a rehash, and this is an explanation. So really, this part, this part, this part, and this is the most important. And that gives us, again, some idea of what the electric potential is. Now, notice when I say electric potential, I stopped right there. I didn't say electric potential energy. Electric potential energy is U. Electric potential, or just potential, is V. So just as a little crypt note, if you will, I'm going to write that down. And again, I evidently expanded my page and forgot to unexpand it. So I've been writing it as if I was running out of paper. So what I'm going to say is electric. Oh, let's actually write it. So electric potential energy implies U, which is measured in joules. Electric potential, which is also just potential, is V, which is measured in volts, which equals a joule per coulomb. Okay, so these are some big principles you want to do. What I'm trying to also point out to you is, just like when I told you to use Coulomb's law, but don't actually put the charge, the sign, into the Q's. Well, I'm going to tell you, there's a lot of times where I ignore these floating negative symbols in a lot of these definitions, and I use my understanding of how voltage and potential energy are supposed to work. So it might help you if I actually know exactly how voltage and potential energy behave. So I'm going to restate that. Okay. Potential energy changes on its own. In other words, the potential energy of an object will change all by itself if given the chance, if you go from high potential energy to low potential energy. In other words, just like the second law of thermodynamics, where I said heat flows spontaneously from a hot body to a cold body. Well, objects flow or move spontaneously from high potential energy to low potential energy. If you want to go from low potential energy to high potential energy, you're going to have to do some work on the system. Now, as far as the voltage goes, which is electric potential, but not electric potential energy, positive charges go from high potential to low potential. So on their own, positive charges go from high potential or high electric potential or high voltage to low potential or low potential electric potential or low voltage. And negative particles go from low potential or low electric potential or low voltage to high potential or high electric potential or high voltage. Okay, so negative charges move the opposite direction as positive charges when you're talking about voltage, but everything moves the same way when you're talking about potential energy. Everything moves the same way, whether it's a positive charge, a negative charge, or a neutral. Okay, so hopefully that little sentence will help you. I'm going to write here. Explained V delta V versus delta U for positive and negative objects. So I just wanted that to be in the notes so you can look at the notes and say, oh yeah, I better turn to that part of the film to find out what we're doing. And of course we started at 12:45, so this should be roughly 1 hour into it. So. All right, any questions on that? All right, I would like to just press on, but I know it's not very nice to give you a 3-hour class with no breaks. So let's go ahead and take 10. It's 11, it's 1:42 right now, so come back at 1:52. I'll be here in case you have any questions. So feel free to ask me any questions you might have while you're here. I'm just sitting here waiting, but I do want to give you a 10-minute break, and I will start counting down when we get to the 150 mark. So 152 is when you're supposed to be back. And I'll be right here. Anybody have any questions?
I don't have any questions.
Okay. I'm going to actually pause the video recording for a little while. Would y'all please help me remember to unpause? I forgot again. All right, it's recording now. Rhea said she had to split. Gotcha. All right. So I just wanted to let you know I've done a recap in my notes of exactly what we've accomplished so far. So I'm gonna go ahead and share that with you, and just trying to give you a synopsis of what the important stuff out of all the stuff I just told you was, in addition to those sentences that I told you were so important so that you'd understand the difference between voltage and potential energy. These are the key results. I wanted to remind you that voltage, based on the definition of it, voltage is like the potential energy per unit charge. And that gave us that the volt is equivalent to 1 joule per coulomb. That's something important we need to understand about what the volt is. Also, in using a very specific result, that specifically the result we got for when E was a constant, we found that the E being the electric field, we found that the units of the electric field can also be written as volts per meter instead of just newtons per coulomb. We also reiterated the fundamental idea of what potential energy is. So the way you can determine potential energy between two locations, for instance, is to calculate the negative of the work done by the conservative force that causes that potential in going from point A to point B. So if you wanted to know the change in potential from point A to point B, that would be called delta U, which is UB minus UA. And that's the negative of the work done in going from A to B, or negative W sub BA. That's equal to negative integral of F dot DL. I've got that written in the next box. Also, I wanted to remind you that for a uniform field, and only for that uniform field, do you generally get the change in potential energy is Q times E times D negative. It's negative Q times E times D. That will come in handy on occasion. We've already seen, for instance, how we could use it. The voltage difference, for instance, between two plates of a parallel plate capacitor. Because in that case, we're going to use delta V is delta U over Q, and you just get ED for the voltage of a parallel plate capacitor. That's exactly right. I then went ahead and wrote that VBA, which is the voltage change in going from A to B, is equal to delta V. That's equal to VB minus VA. That's defined to be UB minus UA over Q. In other words, VB is equal to UB over Q, and VA is equal to UA over Q. That all is equal to the negative of the work done in going from A to B divided by the charge Q, and that is equal to the negative integral of E dot DL, not F dot DL, because the dividing by the Q turned the F into an E, okay? And we use that expression to actually obtain a formula for voltage, for instance. So that's why that comes in handy. Then we went back, or I went back and used what I knew about delta U. Delta U is UB minus UA, which we can take this middle expression, which is UB minus UA over Q is equal to the change in V. And we can flip that on its head and say that the change in electric potential energy is equal to Q times the delta V. And by getting that, I get Q times parenthesis VB minus VA, which is Q times V sub BA, which is Q times delta V. And the main reason I'm pointing that out is because one, that formula Q times VBA, that is a formula that you need to use over and over again, but not only that, the formula looks just like a specific unit that we use for microscopic objects. Instead of working in joules when we're talking about atoms and molecules and protons and electrons and pions and mesons and stuff like that, we actually tend to work not with joules, but with something called the electron volt. And the electron volt is the energy obtained by a single electron in traversing a voltage difference of 1 volt, at least its magnitude. So using that formula, you see that 1 electron volt is 1.602 times 10 to the negative 19th joules. And that's specifically because the charge of the electron is 1.602 times 10 to the negative 19th negative. So charge of E minus the electron is equal to negative E, which is negative 1.602 times 10 to the negative 19th coulombs. We know more sig figs than that. The pictures I have from the inside cover of the hardcover version, the picture that I have of the inside cover of your hardcover text has those values like E and K and epsilon 0 to more sig figs, so you can check that out as well. Anybody have any questions on what we've done so far?
No.
You did, Micah? Or
No.
okay. All right. So after this, your book sort of does the same sort of things that I just did there, and it asks you for a conceptual example. So I'm going to give you the same conceptual question / example and see if you guys can answer it. Feel free to just blurt out the answer or type it into the chat. Either one is perfectly acceptable. What I'm going to say is, suppose a negative charge, such as electron, is placed near the negative plate. So if you look back at this diagram, we'd say the electron's at B. Okay. So imagine putting a negative charge, an electron, for instance, at B in that parallel plate capacitor drawing. If the electron is free to move, will its electric potential energy increase or decrease? So imagine putting an electron right there at B.
Its electric potential will increase, right?
Its electric potential will increase.
Yeah, because it goes from
electric potential. You didn't say electric potential energy. So are you meaning the energy or are you meaning the electric potential?
Wait, sorry, your mic's cutting out. Wait, so electric potential versus electric potential energy?
Right, that's the difference. So what I'm asking you is, if the electron is free to move, will its electric potential energy increase or decrease?
Ah, shoot. Okay, I got
It will decrease.
Very good. It will decrease because the electron is actually not very comfortable being near the negative charges, which is point B, which is at where it's at. So it has a high potential energy in some sense there, just like me being on top of a telephone pole or a turtle being on top of a fence post, right? So it will naturally move away from there. We can think of it in a force perspective as, oh, a negative charge is going to be repelled from that negative plate. So it's going to move to the left and go towards specifically point A, which is where the positive plate is. That will be a decrease in potential energy. And the way Michael was referring to it is he realized that the electron would actually move from B to A and achieve some kinetic energy. In other words, if the electron left B and ended up at A, it would actually have a higher speed at B than it has at A than it has at B. Does that make sense?
Mm-hmm.
That's what you're trying to say as well, right, Micah?
Yeah.
Okay. So that's the big thing. Now, what Michael referred to is actually quite correct. So as I told you in those few sentences or paragraph that I gave you earlier, positive charges move from high electric potential to low electric potential. Notice I didn't say the word energy. Positive charges move from high electric potential to low electric potential, and negative charges move from low electric potential to high electric potential. Again, I didn't say the word energy. So yes, in the electron moving from B to A, its voltage actually increased. And that's what electrons do. They naturally increase their electric potential. But like everything, it also naturally decreases its potential energy. So everybody follow that? Does that make sense?
So is electric potential more like kinetic energy than is
Your
that like
book, that's good that you're thinking that way, because we want you to think in terms of things you already know. Your book makes a point to discuss this in figure 23.3. I can't give you a page number because it's electronic, but it's right before table 23.1. What it tries to make you think of is H, the height of a rock, for instance, is sort of like the electric potential. Whereas potential energy U, which is M times G times H, is more like electric potential energy. So if you bring a big rock up to a height H, then it's going to have a potential energy M times G times H. It's going to have electric potential H. Okay.
okay.
Now, if you bring a bigger rock, say twice as heavy a rock, to a height H, it will have an electric potential energy of, or excuse me, a potential energy of 2 mgh, but it will still have the same potential H.
Okay.
So that's the analog they're trying. So I would definitely take the time to read those couple of paragraphs by figure 23.3. So definitely take that time. I'll write it here.
Figure 3.
I'm saying read paragraphs right before figure 23-3. Okay, so hopefully that'll help you a little bit as well. Your book goes on then to give you some rough estimates now that we've encountered this quantity.
Professor.
Yes.
Yeah, I understand why the answer was a decreased as it left the negative term because like that H it's decreasing, so it's feeling a smaller repulsion from the negative plate, right? Yeah.
Right.
Okay, I get it now.
Yeah. Yeah, and that negative charge is what makes the fact that you have to divide about Q. That's what makes the sign flip and voltage behaves differently depending on what charge you're doing, what charge you're using. Whereas potential energy is always going to decrease naturally. Electric potential could decrease naturally only if it's a positive particle, but it increases naturally if it's a negative particle. So yeah, I think you actually got it.
So sorry. So why do they use such I guess confusing wordage for it?
It's largely because of, it's sort of like if you look at Newton's system of, he called it a system of fluxions, which was his invention of the calculus. He had all these weird symbols and all these weird words because he didn't have any idea what the big picture was going to fall out to be. Leibniz, as best we can tell historically now, Leibniz had an idea what it was all going to be, specifically because someone leaked what Newton had done to him. So Leibniz comes on the scene with these very fancy innate ornate symbols like a elongated S for the integration and a d by dx for the derivative, because he knew the derivative was going to be a slope and d by dx looks like a slope, and because he knew the integral was going to be an infinite sum, so he made it look like a elongated S. That's the difference between hindsight being 2020 versus hindsight being crap, right? So what they did was they made up words with ideas that they thought were relevant at the time, and then later they turned out to be, dead ends basically. So you're left with a lot of words like potential, electric potential, permeability, permittivity, Displacement current's another one. That turns out to be completely wrong, but we still keep the phrase displacement current. So that's what's going on with a lot of terms in general. Historically, you come up with names for things in a time where you think, a particular hypothesis is the case, and then later you find out that hypothesis is completely wrong, but historically the name is stuck.
Okay.
Does that make sense?
Yeah.
All right. So what I was saying is right after that figure 23.3, there's a table 23.1, and the author gives you some characteristic voltage values for various things. So for instance, the typical voltage of a thunderstorm is on the order of 100 million volts. The typical voltage of a high power line, this is the ones that we see going through country fields, for instance. It's like on a big tower that sort of looks like a person wearing a skirt, but with no arms and no head. That big tower, those are made to be very, very tall, so they can carry what's called high tension, another stupid word, high tension, which means high voltage power lines. And those power lines normally carry on the order of power at a voltage of around 100,000 to multiple million volts. So it's not unreasonable to have 10 to the 5th to 10 to the 6th volts for
So
power
is that
lines.
why you hear the sound of those vice like regular power lines going through your neighborhood,
Exactly.
and you feel
Yeah.
the difference underneath them?
Yeah, you can, if you get close enough to them, like when I lived, or when I lived in Chapel Hill, my then wife ran a fitness center at a very luxurious gated community on a mountain. And one of those high tension lines that went over a mountain, went over quote unquote the poor section, and it was probably 25 feet off the ground. And we would walk by and our hair would stand up, and you could hear popping. And like if it's a moist day that's been raining, you could hear pop, pop, almost like one of those mosquito zappers. But yeah, what's going on is when you get that voltage that high, you're pushing the envelope, what's called the electric breakdown voltage. So in air, there's a actual electric field strength where air would just as soon become a conductor instead of an insulator. That happens to around 3 million volts per meter. So that's the electric field strength of breakdown. So if you have a high voltage like 200 volts, then it can go or 200,000 volts, it can go a pretty good distance and actually cause lightning strikes. So yeah, that's why you tend to hear them. Normally they're so high up that you don't hear them, but if you come into an area where they're kind of close to the ground, you'll definitely hear them and see pops and all sorts of stuff. It also mentions your car ignition is it runs on a 12-volt battery, but to be honest with you, they build up a voltage difference when they go to start it on the order of 10,000 volts. You can see that by looking at really the spark plug level. That's where actual lightning strikes, and that's because of a voltage difference of on the order of 10,000 volts. The automobile battery, of course, is 12 volts. I will tell you that typical batteries like AA's, AAA's, C's, and D's, those batteries are all 1.5 volts. That's their nominal value. When you actually go and buy one, though, if you connect it to a voltmeter, even while it's running like a flashlight, you'll find that they typically are 1.65, 1.68 volts. And that's just a little buffer, so it never really drops below 1.5, because once it goes below 1.5, it's no longer the specified voltage that the person designed the circuit for. So yeah, all those AA, AAA, C, and D batteries are 1.5 volts. Of course, the little rectangular ones that you have in smoke detectors, they're 9-volt batteries. I do recommend everybody take a chance to take a clean 9-volt battery and stick their tongue on it. So you can actually feel the voltage. And that actually also is a good test to see whether your battery that you're using is actually a good battery, because if it doesn't burn your tongue very strongly, or doesn't, bite your tongue very strongly, then it's probably pretty dead. I will tell you also that resting potentials across nerve membranes is on the order of 1/10 of a volt. And electroencephalograms, which is basically like brain scanners looking for electrical signals of your brain, they're picturing on the order of 1/10 of a millivolt, whereas EKGs are usually running on the order of millivolts. So that gives you another idea of some values. Now that we have that, let's use this new idea and this new formulas that we have to calculate how much kinetic energy a electron will get by traversing a voltage difference of, let's say, 15,000 volts. So if an electron and I'm writing the actual value of the charge. That's one you should probably commit to memory, by the way. The mass, maybe not so much, but the charge you should definitely know. And a mass, M sub E, is equal to 9.109 times 10 to the negative 31st kilograms. Traverses a path from 0.00 volts to 15,000 volts. How, dang it, that really went badly. How much kinetic energy will it obtain? And B, ignoring, actually, let's start off on another line. Ignoring relativity, how fast will the electron be going? Okay. So solution, what we have here is delta U plus delta K is equal to 0. And we know that delta U is actually going to be given by Q times delta V. And it's actually going to be a negative. Okay. So if I put that in, I will get negative Q delta V plus delta K is equal to 0, or delta K is equal to Q times delta V. Now that's going to be 1 point, that's a negative. Actually, let me give myself more space than that. So now I can say delta K, this is part A, by the way. So delta K is equal to Q delta V, which is negative 1.602 times 10 to the negative 19th coulombs. And we're said it's going to go from 0 volts to 15,000 volts. So that'd be 15,000 volts minus 0.00 volts. I'm going to assume all those sig figs are sig figs in the 15,000. So we actually have 5 sig figs. That's crazy, but that's what we're going to do. And what I get is 1.602 e to the negative 19th times 15,000. And that gives me 2.4030 times 10 to the negative 15th joules. And basically what I did there was I just more or less counted the magnitude. Now, since the charge was negative, technically I got a negative joules, but that was supposed to be the change in potential energy, or the negative of the change in potential energy. The potential energy in going from 0 volts to 15,000 volts should have been a decrease in potential energy. So I was actually screwing up by blindly plugging that negative in, which is why I told you I often just ignore the floating signs on various symbols and then work them out myself. So that's what I'm going to do here. I'm going back now and just saying, okay, well, the change in potential energy is going to be Q delta V. And if that turns out to be giving me a negative change in kinetic energy, I know that's wrong, which is what happened. So now what I'm going to do is I'm going to say, by doing this, we get delta K is actually negative Q delta V, and then that'll make this positive, and then everything's correct. So the change in kinetic energy, or the kinetic energy achieves, is in fact 2.4030 times 10 to the negative 15th joules. And that's part A. Now, by the way, I'll just show you how much nicer that is. We would say that the kinetic energy final is actually equal to 15,000 electron volts. And we'd be done. Okay, that's the beauty of using electron volts as opposed to joules. Now I'm going to do part B. And part B, what we're going to say is K final is equal to 1/2 the mass of the electron times the velocity of the electron squared. So the velocity of the electron should be equal to the square root of 2 times the kinetic energy final divided by m. So that's going to be 2 times 2.4030 times 10 to the negative 15th joules divided by 9.109 times 10 to the negative 31 kilograms. And again, we're assuming a relativity is not relevant here. Definitely at 15,000 volts, relativity is relevant, and we should be using a different formula. In fact, the different formula we should be using is K is equal to gamma minus 1 times mc squared. That's actually the formula for the kinetic energy, but we're just not choosing to do that. When I put this in, I'm going to say 2 times 2.403 times 10 to the negative 15th, and then I'm going to divide that by 9.109 e to the negative 31. That gives me the square root of 5.2761 times 10 to the 15th. And notice joules divided by kilograms is a Newton meter divided by a kilogram. A Newton meter is a kilogram meter squared per second squared. So this is just meters squared per second squared under the square root. So when I take the square root of that, I get just meters per second. And lo and behold, the velocity of the electron is 7.2636. Actually 7.2637 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th meters per second. So it's about, more than 90% of the speed of light by that. So that gives you
Yeah,
some.
I got the same value.
Did you? Okay, cool. Thank you. All right, so that's one of the problems we can work. And not only that, that specifically, if you really wanted to do such an experiment, the way you could do that is you could build a plate, a positively charged, or excuse me, a negatively charged plate like this, and it have a bunch of negative charges on it like this. And you basically do something to compel an electron to jump off of that plate. And then when you do that, that plate is going to be opposite, or have opposite it another plate that's positively charged. And it's positively charged in such a way that the electron has no compunction to go up as opposed to down, or to go left as opposed to right, or to go up into the left as opposed to down into the right. So the electron, which happens to exist right here, it's going to go straight, because it's no better to turn left than it is to turn right. It's going to go straight through this hole. And what you do is you find that this right here has a voltage of 0.00 volts, whereas this one has a voltage of 15,000 volts. And the electron will come flying out of here with a velocity of on the order of 7.2 times 10 to the 7th meters per second. That's exactly what we do when we do the magnetic deflections lab. So I'm going to say like magnetic deflections lab. In that lab, basically, we use two plates like this, and then we use a very high voltage source that puts out up to 5,000, 6,000 volts, something like that. And we use that to basically put a voltage difference across these plates. We generate the electrons, and then the electrons fly through that hole, and then we send them into this area where the magnetic field is very strong. So the electrons come in and they leave a little blue trail, so we can actually watch the little electrons in some sense moving, because we can see where they've been due to the little blue trail. And it'll come in and then enter the magnetic field and curl. So it'll start to rotate around, and we can figure out the radius of that circle that it's making, and from that determine the charge to mass ratio of the electron. So that's what we're going to do in a later lab called magnetic deflections. But that's a real life problem. It's kind of helpful. Anybody have any questions on that?
No.
All right. I will tell you also that you can use this to, for instance, compute the electric field between two plates. So let me show you another example. I'm going to do this, and I think this might be the last one. I'll let you guys go since we're doing it beyond our normal time. We're supposed to run until 2:50 when lab is over. So I'll try to be respectful of your time and definitely not go over, but I'm probably going to give you a little bit less than going till 2:50. So what we're going to say is two parallel plates are separated by a distance of 1.00 millimeters, and they differ by, let's say, 150 volts in electric potential. What is the magnitude of the uniform electric field between the plates? So that's our question. Here's our solution. What we know is that delta V is equal to E times D. Okay, we know that from the derivations we did early on when we were inspecting delta U as UB minus UA, and we ended up getting QED. And then we found out that voltage was delta U divided by Q, so we just get ED. So with this in mind, we can say that E is going to be equal to delta V over D. And delta V, of course, is 150 volts. I'm going to assume that's 3 sig figs. And then 1.00 times 10 to the negative 3. And the wheels just fell off right there. So times 10 to the negative 3 meters. And what that's going to give us is basically 150 times 1,000. So that'd be 150,000 volts over 1.00 meters equals 150,000 volts per meter, or the electric field strength is approximately 1.50 times 10 to the 5th volts per meter. Now, just so you'll know what that looks like, we're actually talking about, for instance, a positive plate, a negative plate, 1.00 millimeters. And if we connected this to a voltmeter, we would say this is our V port, and this is our COM port, like that. And we would connect the COM port to this one. And we would connect the V omega port to this one, and it would read 150 volts. Okay, so that's what we're talking about. A parallel plate capacitor like that, the voltage difference being 150 volts, the difference in distance being, or the separation between them being 1 millimeter, and we get a very large very large electric field of 150,000 volts. Anybody have any questions on that? Now, looks like no one does. All right, let me do this one little thing here. So something else that's kind of neat is we know that V, I've sort of done this, but actually, no, I shouldn't. I haven't done that yet, so I don't want to really go there. What I will do is remember that delta V, which is supposed to be VB minus VA, which equals VBA, is defined to be the negative integral from A to B of E dot DL. So what I'd like to do is calculate the voltage difference between, let's say, between a particular point in space and the center of mass of a conductor of charge Q. So what I'm going to do is I'm going to imagine a coordinate system right here. There's my x-axis, there's my y-axis, there's my z-axis. And what I'm going to do is I am going to put a sphere centered at the origin. This is a sphere whose radius is r and whose total charge is q. And what I would like to know is what is the voltage at that point P. So for R less than R, for R equal to R, and for R greater than R. And actually, I should probably do them in the opposite way, but or in the opposite direction. In other words, do the far one first. Darn it. Do the far away one first, and then do the equals, and then do the inner one. Darn it. It's aggravating me. Okay, so what I know is I can imagine integrating along a very specific path. So this line is going to be my very specific path, and way out here at infinity, I'm going to have V equal to 0, because you're allowed to call the 0 of potential energy anywhere you want, and this is electric potential, so I'm going to assume that the same thing applies to it, and I do know for a fact that it does, so I'm going to do that. So what I'm going to do is I'm going to calculate VBA, which equals the negative integral E dot dl. And again, this is a surface, or excuse me, a path integral. So I know the electric field due to this is actually given by Coulomb's law, and that is Q over 4 pi epsilon naught R squared. Now it points in the R hat direction, which, remember, any point X, Y, Z, if you draw a line connecting the origin to that point X, Y, Z, then a line from the origin to that point is parallel to R hat. So that's what I mean by the R hat vector. And I'm going to use the actual DL vector to dictate which direction I'm going. When you're doing a line or a path integral, you have to either allow the DL to show the direction you're integrating, or you have to allow the range of integration to show the direction you're going. Once you choose one, the other one just has to go in the positive coordinate direction. So for instance, if you're going from x equals d to x equals 0, in reality, that's what you're integrating, then you can integrate from d to 0, but you would call your DL, even though you're going in the negative direction, you're going to call that dx I hat. If you want to use your DL to tell you what direction you're integrating, then you'd use DL as negative dx I hat, but you'd integrate from 0 to d. So that's what we got to do here. I'm going to use my DL to specify direction. So I'm going to say this is dot dx I hat with a negative sign in front of it. Okay. Now, the way this works, as we've learned with dot products, they are linear operators, so we can pull out the scalar parts of them. And in fact, these scalar parts are negative, a cube, a 4 pi, and an epsilon naught. And then I'm going to have an integral of negative dx, or excuse me, that should have been dr. Sorry about that. Since I'm actually going in a radial direction, that should have been called dr, and this should have been called r hat, not I, because I just was remembering the special example I gave you of moving along the x-axis. So this is going to be dr r hat. Okay, that negative came from the DL, and I've got dr over r squared, and then r hat dot r hat. But of course, r hat dot r hat's just 1. This gives me positive q over 4 pi epsilon naught integral. Now, since I did specify the direction I'm going by using the DL vector, then I just point in the positive coordinate direction. So I'm going to say from R A, or excuse me, from RA, which I'm going to say is smaller than RB. So RA is less than RB is where I'm going to. So I'll say this distance right here is RA. Okay. So I end up getting that times r to the negative 2 dr. And of course, the integral of r to the negative 2 is negative 1 over r. So now I can write this as negative q over 4 pi epsilon naught. Now I'm going to say that negative took care of the negative from the integration. I now have 1 over RB minus 1 over RA. Now that is supposed to be equal to the final voltage, which would be VB, minus the initial voltage, which would be VA. If I take the limit, if I want to calculate V at A, to calculate V at A, I'll take the limit as RB approaches infinity. So that's what I'm doing there, is I'm actually going to take the limit of this as R approaches infinity, and that really turned out horribly. Okay, so what's going to happen is I'm going to get VB minus VA is equal to negative Q. I'm really having a hard time fitting this on here. Tell you what I'm going to do. I'm going to copy it over to the next page and just finish it real quick, and then I'll let you guys go. Copy, paste. Okay, so I got everything I need there, probably some extra stuff too, but VB minus VA, I'm going to go ahead and put this somewhere useful. I'm going to say taking the limit as RB approaches infinity. And what that's going to give me is VB minus VA is equal to negative Q over 4 pi epsilon naught times the limit as RB approaches infinity of 1 over RB minus 1 over RA. So you can see that VB minus VA is equal to negative Q over 4 pi epsilon naught times the limit as RB approaches 0 is 0, and then minus, actually, that last bracket should have been to this side, minus 1 over RA. Okay, so what we actually get then, I did that in the right order, VA negative, yeah, that all works out there. Okay. And did that negative. I'm just double checking my signs here. Positive R to the negative 2, that works right. I need to do that. The electric field's actually pointing out, so that did fine. So VB minus VA, we can see that the VB corresponds to 0. We can see that the VB corresponds to 0, and we're going to say the VA corresponds to Q over 4 pi epsilon naught RA. So that's RA equals R, which is greater than big. Where R equals big R, we get V is equal to Q over 4 pi epsilon naught, just plain R, which I'll call like this, and this is for R equal big R. And now we're going to do for R less than big R, then what we know is delta V is equal to the negative integral of E dot dl. But since this sphere is a conductor, since that sphere is a conductor, we know all the charge is going to be on the outside. And in electrostatics, that also tells us the electric field inside is 0. So we're going to take this and say equals negative integral of 0 dot dl, which equals 0. But remember, delta V is going to be V at R less than big R minus V at R equals R. So we got V at R less than big R minus V at R equals R is just equal to 0, which means V at R less than big R is equal to V at R equal to R. So V at R less than R is equal to Q over 4 pi epsilon naught R. And that's the answer. And that's the answer. And that's the answer. Okay. So that's it. I'm going to call it a day on that one. Only let you out 5 minutes early, but we did start a little bit late, I guess. So thank you for coming, everybody. I have moved the dates for chapters 22 and 23. 22, you should have been able to get done already, but I still get you a little bit more time. But 23 will not be due until Sunday of next week. So not this Sunday, but next. And we are shooting for our test to be this coming week. And I will be posting a online test probably today or tomorrow. I'll let you know when I get it. Have a good one. Thanks for coming, Aaron and Micah. Y'all have any questions for you, Split?
No, I don't have any questions.
All right.
Yeah.
Well, thanks, guys. Appreciate you showing up.
No problem, Professor. Have a good day.
You too.
And I'm gonna finish those modules that I missed. So
Okay.
yeah,
Let me know when you're
spe-
done, and I'll see what I
yeah, I'm
can do for you.
spending. Yeah, I'll spend like this week too. Oh no, for like the Pearson modules, you don't have to move the date back from it. It's just the test.
Oh, okay.
I
Gotcha.
gotta take. Yeah,
Yeah, gotcha.
yeah, that
All
kind
right,
of thing.
no problem.
Thanks for.
I'm going to open up the practice test too, since you're taking that test.
Yeah, I was
I'll
gonna
be
say too.
open that for
But
you.
what I'm doing is I'm going through the chapters like 19 and 20, 21, and I do like the Pearsons like after I finish studying. Like I do all of the big questions that they show in the chapter. Those are really useful, and I know you do some of them in class.
Yeah,
So
that helps a lot.
yeah.
All right,
All right.
have a good one,
Yeah,
Micah.
I'll see you younger. Yeah.
See you.